Yeah, so welcome to our event on committed sea level rise from Greenland at today's 1.1 degrees Celsius. And the speaker for today is Jason Box. Okay, so yeah, so Jason Box, he is from Geological Survey of Denmark and Greenland, and he has been working on Greenland ice for more than 30 years. And yeah, we will have Q&A session in the end, and for those participants attending virtually, you can send your questions in the chat. Yeah, welcome, Jason.
Thanks so much. So I'm going to be talking about how much ice Greenland is already committed to lose in the coming time, and then zoom out to what we have in store. How does that ice loss commitment change into the future? We just published 2.5 months ago this ice loss commitment, where using observations and robust theory, we find that at least 3% of Greenland ice is already in the pipeline, ready to go into the sea. It's just a matter of time. So I'm going to give detail to that, explain the methods, and then zoom out to related aspects. So I want to start with this cartoon profile of an ice sheet. And the key factor you can see is the snow line that divides the area that's accumulating mass and that which is losing mass. And snowline is this really important integrator of the competing effects of mass gain and mass loss. And the ice sheets and glaciers, that's really fundamentally what we're focused on, is the balance. How much are they growing or shrinking? And the snowline integrates that. And the snowline moves up when there's a warm season. Snowline is measured at the end of the melt season. And then by the time winter comes, the surface becomes blanket again with snow. The same kind of picture, we can observe the position of snowline with photographic images from satellites. Just based on a threshold in the reflectivity of the surface, we can classify the area that is dividing the part of the ice sheet that's gaining mass and that part that's losing mass. What you can see here is a low melt year. So the snow line is low and the area accumulating mass is high. So here's a high melt year. And when I compare it with the low and the high melt years, you can look around the ice sheet and see how this snow line is changing from year to year. That same ice sheet profile, and then the graphic above illustrates the observed mass balance on the horizontal axis. You can already see that the average mass balance of the Greenland ice sheet is about minus 270 gigatons per year. That's equivalent with all people on the planet having a bathtub of water every day of the year. Over that period of time, this is a 20-year sample. On the vertical axis, you can see the area that's accumulating mass. And as you saw before, when there's a high melt year like the lower left dot, the ice sheet was losing more than 400 gigatons that year, and the accumulation area ratio was low. As you can see, the sample of measurements from the satellite optical data show that the accumulation area ratio and the mass balance have some correspondence between them. And a statistical property of the data, you can see the intercept of the fit at mass balance is 0. In a condition of mass balance, what is the AAR? Projected below, you can see how the equilibrium AAR, or the equilibrium snow line, is at a lower position than the average. So in this past 20 years, the snow line of the ice sheet has climbed upward. Any ice mass that has surface melting, under the effects of surface melt, will adjust its shape to try to be in equilibrium with the position of the snow line. It's also called the equilibrium line and the equilibrium line altitude. And so long-standing observations and robust glaciological theory shows that this ELA position, and here it's corollary, the AAR, tell about the health of the ice mass. When the study came out, a journalist asked if this committed ice, if he should call it zombie ice. And I thought that was a fair point, because this ice has not yet exited the system. It's committed to be lost. It is in the process of being lost. But with the elevated snow line, the shape of the profile of the ice sheet needs to readjust by losing that section of ice. So it's got 1 foot in the grave, this ice. The bottom lines that I mentioned, we find a committed area loss of at least 3%. The actual shape profile of the ice sheet gives an exponent of 1.24, and that goes down here in the bottom where we scale from area to volume. But for the mathematics to be analytically proven, you need to use an exponent of 1. That's the small gamma number in the bottom, where you're scaling from area change to volume change. When the observed area to volume ratio has an exponent of 1.24, closely matching the theory of 1.25. And so that means that the number that we published, 27 centimeters, should be about 20% higher. It just that the math can't be proven with a nonlinear exponent, and we didn't want to perplex the review process too much with using the actual exponent. So the number is higher, but only by about 20%. It's not very good news, actually. In the upper left, again, I'll draw your attention to the red dot. It's the year 2012. It was a record melt year. The mass balance of the ice sheet was more in deficit by more than 400 gigatons, and the AAR was around 0.84. When we take that year in constant as a representation of the future climate, it suggests a committed loss of 78 centimeters of sea level rise. Something we didn't put in the article that got published, we thought it was too much, but we found a way to scale the commitment into the future using the observed fit with summer temperatures. So because the Greenland summer temperatures fit with the AAR as well, these are the high emission scenario in red, where sea level rise commitment, not sea level rise, but the commitment to it rises above 1.5 meters. And the blue curve is a kind of a Paris-like climate scenario. And so optimistically, Greenland has a commitment in the future, probably around 1 meter. How much time it will take, this approach doesn't deliver. However, the last paragraph of the study, check it out. It's open access. There we cite 4 observationally based studies that find ice moving faster than conventional ice sheet models can move ice. And therefore, we argued that the majority of the sea level commitment up to present should be delivered by end of century. The majority of, so 2/3 of. I'll talk more about that in some following slides. I just want to draw attention to what the 6th assessment report for the IPCC had for the sea level rise for Greenland. In the high emission scenario, the AR6 IPCC report has 12 centimeters of sea level rise from Greenland. In a Paris-like scenario, something like 6. And I'm going to call those into question as I draw the slides, as I go through the slides. First, by a kind of apples to oranges comparison. Now, I'll come back to that. The apples oranges is now, if we put our sea level commitment on the same scale and recognize that our numbers are up to present, that is up to the year 2019, that sea level commitment that's already committed is more than a factor of 2 higher than the high emission scenario AR6 climate models by end of century. So these numbers are in a completely different ballpark. And I don't want to discredit the ice sheet modelers, because there's a lot of clever people working at it, but as I'll highlight later in the presentation, there are a number of known ways that ice is moving quickly that are not yet encoded in the models. Why are they not yet encoded? It's very challenging to articulate the physical expressions for what we observe in the field. And I'll talk more details about that. To the IPCC's credit, and I think the writing is excellent. I think the way that they've tried to deal with the uncertainty in sea level projection was as good as you could expect. And they did include this low likelihood, high impact scenario, which now this is global sea level rise. And it comes down to there being a 1 in 20 chance of there being 1.5 meters of sea level rise by end of century. And one of the authors of the studies put it like this: if there's a 1 in 20 chance that when you cross the road, you'll get struck by a car, do you cross that road? And I thought, well, it's kind of like if there's a 1 in 20 chance your plane would crash, you would not get into that plane. And that risk framing lays bare how we're not treating the low likelihood, high impact events in our policy, in the policy that we've had so far, because the climate policy and our simple risk management approach to this does not reflect a kind of a sane risk management strategy. So I updated temperature reconstruction that I published in 2013 for Greenland up to 2022. And what that suggests is that Greenland's summer temperatures have increased by 1.2 Celsius above pre-industrial. And just yesterday, because you may have heard of the North Atlantic Oscillation, it's like the El Nino of the North Atlantic. It's called internal variability. And there's actually a more precise atmospheric oscillation that better captures Greenland summer temperature, and it's called the Greenland Blocking Index. So consider it something like the North Atlantic Oscillation or like the El Nino Southern Oscillation. It goes up and down unpredictably. It's internal variability of the climate system, and it happens to be an excellent predictor or a good predictor of Greenland summer temperatures. And this is only to say that it goes far to explaining Greenland's summer temperatures. So that statistical fit, you can detrend the Greenland summer temperatures, and you can see that since about the year 2000, this atmospheric teleconnection, the Greenland blocking index, without it, it would not explain the observed warming very well at all. And it's just to say that the summer temperatures depend strongly on there being an atmospheric circulation that's set up that will drive south air onto Greenland. When you look at the period before 2000, this blocking index wasn't as effective it didn't explain as much of the variance. And another study by Alstrom and others shows that the variability of air temperatures jumped at about this time. And we see more extreme events, not only around Greenland, but Europe, around the world. And this appears to be related to the planetary wave, the so-called jet stream or the Rossby wave becoming more variable. And that relates to increased extremes. And it's part of the story here. So that I'm having a delay on the slides. Greenland summer temperatures, you saw that already. That's the 1.2 Celsius of warming. Then we have the projected summer temperatures for Greenland only from the CMIP 6 in a high emission and the kind of Paris-like emission scenarios, where you can see that according to the model projections, end of century Greenland temperatures should be at least 4 Celsius above pre-industrial. And remember that number 4 Celsius when I'll talk about what is Greenland's threshold for irreversibility. So yeah, irreversibility, elevation feedback. Some cartoons of the elevation feedback. Time 1 on the left, you've got an ice sheet profile, and the red line, the melt area, thinning due to surface melting and from the accelerated flow of tidewater glaciers. So-called dynamic thinning draws the surface down into a warmer part of the atmosphere. That increases the melt area because the ice sheet profile is parabolic shaped, and so you actually get a nonlinear increase in the melt area. It's an exponent of 1.4, so it's not, but it is nonlinear, and it's an example of an amplifier that due only to surface thinning will ensure more surface melting. And this elevation feedback, let's look at in more detail. Levermann and Winkelmann put this complicated graphic together where you have this, it's kind of looks like a hill. And so if you have temperature on the horizontal axis, that is warming up to a critical temperature, TC. That's the tipping point for Greenland. And so here we are, still probably to the left side of the critical melt threshold for Greenland in this stable state. And so the temperatures can fluctuate left, right, or warm, cold, I should say. Oh, I had some, sorry, I'm just waiting for the slides. I think the slideshow is too heavy because I have a bunch of movies coming up. Oh, I want to go backward. Oh, he's helping me now. Yeah, let's go one back. Maybe I can advance it from here. So Robinson and others illustrated the same. Now let's go. Can I just take us back here? Okay, so we're still in the current ice condition. We've not yet crossed the critical temperature threshold on the right, TC, and we can warm and cool the surface climate without tipping over. And the analogy I've heard recently, you know, the road runner and the coyote, they run off the cliff, and if they don't look down, they can run back onto land, no problem. And we can do the same thing with an ice sheet. You can have a crazy melt event like 2012. It melted across the total surface, and it's okay if as long as the temperatures come back, and the road runner and the coyote run back onto land, no problem. But if you stay out there too long, so if we elevate the temperature above pre-industrial for long enough, then the elevation feedback can do its thing, leading to enough thinning that you jump into the unstable state where once you're over the threshold for long enough, then you're stuck. And it doesn't matter if you fluctuate and you run back on land because, well, by that time you're falling. And this graphic is kind of re-illustrated in the following. So the same concept, it's called hysteresis, where you get irreversibility. And so we're gonna go around this curve clockwise. Notice on the vertical axis is the volume of ice, up to 4 million cubic kilometers from Greenland, almost. And so temperatures can fluctuate, and we can stay in the high volume scenario, that is high ice volume, not sound volume. But then we can tip over. I think it's the little animations that it doesn't like as well. And then there is this collapse. So that's at a temperature above, say, pre-industrial. And as you can see from the horizontal axis, Robinson had this at about 1.6 Celsius, and there is the collapse. And then you're down at a low volume state, and then if you cool, you cannot climb back up this because it takes a long time for ice to be regrown. So it's a slow regrowth of ice, and especially to get back up to a large volume. So yes, Robinson and others put their best estimate for Greenland's threshold of viability to be the median of this curve, 1.6 Celsius. So by my estimates, we're still at 1.2. We can still save the Greenland ice sheet. If we could implement a rapid carbon emissions reduction and do a lot of carbon dioxide removal, that could do it. And we might stay we might not lose the Greenland ice sheet. But because that is a probability distribution, the threshold could be lower, it could be higher. 1.6 is just the best estimate. But if we rocket up to 4 Celsius by end of century, chances are we will for sure have signed the death certificate for Greenland ice. And this is pasted from this study, embedded the results from process-based models into a simple analytical framework. That was from Laverman and Winkelmann. It's one of the best studies I've read recently. I really think it's brilliant. And they have a simple equation for the melt elevation feedback of the Greenland ice sheet. embedded the results in process-based models. And what worries me is that the models don't have all of the sensitivity factors in them. So I'm going to eventually get to a tour of those sensitivity factors. So I posed the rhetorical question, faster than forecast? And they write, even for extreme high temperatures, however, our results show that complete disintegration within the next 2 millennia is unlikely unless ice dynamics become dominant or the melting sensitivity is significantly higher. I would debate this statement. I'm going to show examples of why melt sensitivity is higher. And, well, the dynamics, I don't think they'll become dominant, well, unless, you know, the northeast Greenland ice stream started to collapse. I guess we'll just have to wait and see about 10 years. And I don't think it'll be much longer until we know what's going on with the northeast Greenland ice stream. I think it might be movie time, and that's why it's slow. Okay, so here we go to the largest Greenland glacier in some metrics, the world's fastest continuously flowing glacier, the Jakobshavn Isbre, or Ilulissat Glacier, I like to call it, because Ilulissat means the place of icebergs. And what happened, and what totally surprised the science community in the mid-2000s, was a Manhattan Island-sized disintegration of this ice shelf. And it wasn't until 2008 that it was understood it was an ocean trigger. Warm ocean currents had undercut, destabilized this glacier. It melted the ice right at the grounding line, the most sensitive place to do that. It removes friction, and this thing disintegrates from loss of friction. That it's really hard for ice sheet models, even in a perfect ice sheet model. The grid resolution of the ocean is 100 kilometers. And so delivering ocean temperatures precisely to the ice sheet models of Greenland is kind of impossible, or requires a parameterization. And so it's not the fault of the ice sheet models that they're not moving the ice fast enough because of ocean trigger effect. Nonetheless, this ocean trigger effect isn't in the climate models. And what we can see is that a large area of ice can break away in a few minutes, and it takes days to regrow. And that's just a metaphor for how ice is lost faster than it's grown again. This is the Jakobshavn Glacier, and yes, the ice will flow back in, but a retreat and disintegration happens much faster. I think this analogy you can also see in ocean sediment records over the past 800,000 years, where you get a very rapid sea level rise and slow sea level drawdown as ice ages come on. So it's a sawtooth pattern. And I think it has a lot to do with how ice can be lost much faster than it can be regrown. Next slide, please. And so a useful way of continuing this story is to follow the water. We often say, to understand what happens in politics, follow the money. In this case, to understand what's happening glaciologically, let's follow the water. So you might start the story up high, where there are hundreds of surface meltwater lakes like this. They're natural, but they are forming earlier. They're draining earlier. They are solar collectors. That the bottom of the lake is melting 40% faster than the surrounding ice because of the heat absorption within the lake. This maybe minor effect isn't yet in the climate or the ice sheet models. It's an example. And when the lakes drain, and practically all of them do, they deliver tens of millions of cubic meters of water within hours to the bed of the ice sheet and inside the ice sheet. The water temperature is several degrees warmer than the ice temperature, so it heats the ice internally. Trying to advance the slide. So the lakes have an internal heating effect, and warmer ice is softer and it deforms more readily. Some have called this thermal collapse of ice, and to my knowledge, it's not encoded in the ice sheet models. Next slide. So this cartoon, you can see the lake and the water making its way to the bed. The next effect is some kind of lubrication of flow, and GPS set up on the ice indeed show the ice accelerating when there's extra meltwater and also when lakes drain. And the abrupt process of lakes draining is an acceleration factor that's not in ice sheet models. Some debate about self-regulation from the basal lubrication, but that actually is happening higher inland. The basal lubrication is still important. This is a picture of a very wide tidewater glacier, and the dark brown water is evidence of the water that's been moving under the ice sheet rising up when it gets into the seawater. The fresh water is lighter, and so the water is rising immediately at the front of the calving face. The next slide. Oh, no, there's a movie. This is a good movie, or an interesting movie. So what do we see? You see this bay, this embayment, and the meltwater plumes rushing up in front of them. And the fact that the calving or the retreat of the ice front is strongest in the embayment probably has a lot to do with the fact that there's a lot of heat exchange that's being forced between the ocean and the grounding line of the ice. And there you can see the turbulent effect of the sun, or the sun, not the effect of the sun, the turbulence in the water as reflected by the sun. The next slide shows that a bit more steady of a shot. This is a very turbulent environment, forced convection, much more efficient at heat transfer. And it's just driven by the fact that the fresh water is less dense. So it's rushing up from 1, 2, 3 or more 100 meters below. And this cartoon illustrates the typical situation is 3 to 4 Celsius Atlantic layer, so-called Atlantic layer, the red arrows. It's typical that the sea is that warm at about the depth of the grounding line, and the meltwater that's rushing out from below entrains this warm water and forces a heat exchange at the grounding line and along the vertical face. It makes me wonder if that same forced convection is happening in Antarctica as well, because they're very deep glaciers, and if the water temperature is warm at depth, and here this is forcing a heat exchange at the grounding line. Another factor is another factor not in ice sheet models is how water is heavier than ice, and when it ponds in rifts and crevasses and fractures, it exerts more pressure at the depth of the crack than the surrounding ice. So it can open up fractures with unlimited capacity as long as it's kept full of water. And in the ice shelf, the Petermann ice shelf in northwest Greenland lost 2.5 Manhattan Island area in a record warm summer of 2010. And then 2 years later, in the next slide, another Manhattan Island-sized area breaks away. And because of the meltwater ponding, it's a similar effect that's been observed into Antarctica of hydrofracture. It's hard to confirm that in the field, and it's not in ice sheet models. Here's what happens when it's cloud-free for like 2 months in the lower part of the Greenland Ice Sheet, the lower elevations, the surface gets extremely dark. And this, we didn't understand why this was until 2017, or we didn't publish until 2017. It's biological. This ice microbial darkening is not in ice sheet models used to project the future. And in the next slide, you can see what these guys look like under a microscope. And then if you click forward one, these filaments, these linear shapes you can see very closely, they are chains of single cell plants that use a kind of sunscreen to regulate photosynthesis. And the dust particles, which are also there, they are relatively clear, like quartz, and they're actually providing the microbes phosphorus. So yes, indirectly it's dust, but the actual darkening factor is kind of a biological X factor that is not yet quantified. How much more melting will these guys deliver, and is pollution fertilizing them? Open question. And as snowline goes higher, will these guys colonize a larger area and add yet another amplifying effect that can produce faster ice loss? So I'm coming back now to, in the final slides, to talk about how, based on the observed thinning, this is the last 20 years of elevation change or thinning, you have widespread thinning, the Jakobshavn glaciers, where there's more than 370 meters of thinning in 20 years. And using a lapse rate in temperature, that corresponds with an increase in summer temperature in that area by 2.5 Celsius. Or in the square area, it's an average of something like 170 meters of thinning and 1 degree of summer warming. So this is an amplifying effect that's on top of just the general warming, because it has an associated melt increase. So the melt elevation feedback it's really has begun and is reinforcing just background warming effects. Zooming out to the Arctic, orbital changes were taking us into the next ice age. This is a summer temperature reconstruction, for the almost 2,000 years, published by Kaufman and others. So summer Arctic temperatures were decreasing. You can make out the medieval warm period, the Little Ice Age, and then industrialization. And the observations come on as the red curve, and this shape has become known as the hockey stick. And implicit is the industrialization, the overloading of the atmosphere with carbon has prevented the next ice age. And that is published by others. There's actually articles, technical articles published concluding we've stopped the next ice age. But of course, we're rocketing into a super interglacial state for which there is no analog. And while another ice age would probably also threaten civilization, this warming, as you know, is also threatening civilization. And I was surprised, maybe it is in the latest IPCC report, I should check, where you add the next 100 years to this same graphic. So that's the next slide. Get ready. Add 100 years of projected warming. And so the high emission scenario is the upper curve, and the Paris-like scenario is the lower curve. I suspect the true 2100 year will be somewhere in between. But clearly the Arctic is just, the rocket is just off the launch pad, and within our lifetimes and our kids' lifetimes, they will bear witness to, you know, such a climate disruption that I hope the negotiators in the other room can hear this. I think they're starting to get the message. You've got to put it in ways that even politicians can understand, and then it'll we are seeing progress. It's just more of a question of will it happen soon enough before things get out of control. The last 20,000 years of sea level, we have a very stable sea level during the Holocene. This is a time when civilizations developed, cities developed, and part of the success of humans was having a stable climate and a stable sea level. It allowed civilizations to develop. It was convenient that the sea level stayed there all the time, every year, and the rainy season came more or less in the springtime, and that stability is going out. The next is to illustrate what Clark and others published in Nature in 2016. Constant 1990 emissions and Big Ben for scale, and a kind of business, what used to be called business as usual scenario. The world needs to prepare for multiple meters of sea level rise, even with constant 1990 emissions, which is low compared to what we're already doing. So the likely future is somewhere in between. And if you consider the age of a city like London or Dublin or Shanghai, they've been there for centuries. And what about the next centuries? And to make it a little bit more grim, we're almost done for the day here, I hope. Geologic evidence suggests that at this level of CO2, sea level should be about 20 meters higher than today. It's a rough approximation, could be wrong. Maybe it's only 10 meters of sea level commitment. And I tried to upscale here, just a few slides remaining. Not as common knowledge as some things, but I think one of the most important graphs you might see is because of the hundreds of billions of tons of mass that are being removed from the polar ice sheets and Alaska and Patagonia, you can see it actually changes the gravitational field slightly, but it means that global sea level rise is non-uniform just from this effect. It's non-uniform for other effects as well, but the average global sea level rise is the green curve. So when we talk about, 10 centimeters, 20 centimeters from Greenland, it's 50% higher on this contour. And global population is concentrated where the gravitational effect of sea rise is amplified. To draw it a little bit more home, here is the Nile River Delta with 2 meters of sea level rise. So when could this happen? 2050 or 2150, sorry. I think about 100 years from now, if I was a betting person, I think a lot of the Egyptian cotton that the world loves so much would is at risk. And this kind of scary risk flooding map is you can actually go to climatecentral.org and make your own maps of anywhere in the world at any level of sea level. So it's quite a nice resource that they've produced. And then I'll end a few relatively good news slides that I just found out yesterday and this morning. You know, I was like trying to finish my slides like they're ever finished. And Greenland's actually a bit more resilient than the Arctic. So the next slide is the global to Arctic temperature. And the Arctic I've defined here is just north of 65 latitude. And the slope of the line is 2.9x global or Arctic. And the next slide is Arctic Ocean, which is a bit higher than the Arctic, just underscoring how Arctic warming is more concentrated over the oceans than over land. And that's shown in this map. Arctic Ocean warming is something like 4 times global because that's where sea ice is declining. Greenland, you can already see here, it's got relatively light colors. So Greenland isn't warming 4 times the global rate. It's more like 2 times. So that's the good news that I'll end you with today. Thanks for sitting through the rather long slide deck. And yeah, thanks for being here. And let's prepare for an uncertain future.
Thank you. Does anyone have any questions?
That's great. Let's go for dinner.
Just a very quick one, Jason.
Yeah.
That's a great tour. Thank you. But I think you showed it in one of the earlier talks today as well, the plot where you've got the temperature rise and you've got the climate projections and the observations sit slightly below. I just wondered what the explanation for that was.
I don't have an explanation for that. It's either that I glossed over it, but he's got sharp eyes, and it's either that the global climate models are overestimating Greenland. I suspect that's it. It might be the fact that they have a rather coarse grid resolution. I did carefully mask out Greenland from the data, but it's a 2 degree grid resolution. I think it doesn't resolve that. Maybe if the GCMs aren't doing the sea ice decline fast enough, that might be part of it. I don't have a good answer for that, but just got that result a few days ago, and so we're actually working on it in a review article. It'll just be a vehicle to think it through and to see if, but it is quite conspicuous. So the Greenland warming in summer wasn't as large as the global climate models were, and we don't know why. So it's potentially some good news for Greenland. Yeah, for example, like in warm years, something else not in the climate models is the upper parts of the ice sheet get more bright in warm summers because of more frost deposition. So there's at least 1 or 2 damping feedbacks that help sustain Greenland. Perhaps also that Greenland blocking index is part of that story.
So about the sea level commitment of Greenland so far, that is much higher than the higher scenario. So I was wondering, do you think it is a problem of initialization of ice sheet models that do not have the right temperature profile within the ice, that underestimate so much the baseline from which we are starting from?
I'm not an ice sheet modeler, and they probably don't like me very much because I'm like, but that's not included and this is not included. I've made a list and it's something like 12 factors that are known that are not included in the ice sheet models. So the temperature profile, that might be yet another one. And this isn't a criticism of the people that are doing ice sheet models, and maybe they can take the criticism, I don't know, but it's not easy to do that. Otherwise it would have been fixed already. I mean, the list of issues I've got in a document that, and we delivered that to the Danish National Climate Research Center, and they're kind of seeing if they can work on some of those and to prioritize them, because they are actually proactively trying to put resources where the biggest questions are.
Because actually, well, I am an ice sheet modeler, definitely, but I'm a paleoclimate ice sheet modeler, so I've been looking at ice sheet dynamics with different climatic contexts. So that's why I'm asking the questions, because one of the tricky points for ice sheet projections is to initialize the ice sheet model long enough so the entire ice column got somehow the right thermodynamics to model the viscosity of the ice right, and so it can react properly to the climate fluctuations. And if it's too cold, for example, the velocities are too slow. If it's too warm, the velocity are too fast. So I know that this is one of the main tricky points of our projections in the future, this initialization.
I think that's is that not a longer term, or it's very, very important on long millennial timescales. I think the critique that I'm mainly listing about the ice sheet models is can they deliver ice in a few decades? Yeah.
Yeah, but the thing is, if you want to simulate from now, let's say in the future, you need to start initializing the model well before. So the long term before nowadays is important to have the right velocity with the right climatic history embedded within the ice. So that's a big discussion. It has always been a big debate, and a similar debate is in the ocean community to spin up the heat correctly so they have the right thermal line circulations. So nowadays we use some tricks in the ice sheet community to spin up the entire heat over the ice and to have a state of ice velocity that reflects what we observe with satellites. But normally you should spin up from, I would say, the last deglaciation to have a proper climate history and evolution of the ice viscosity that then can properly react to the climatic fluctuation at shorter time. So I think I would see that as a major problem. Try to ask that to the ice sheet model community about spin up of the ice sheet model.
Yeah, yeah.
Thank you. Yeah, just a question. I know you were saying just on time frame commitments and saying that by the end of the century it might be more like a meter of sea level rise. But in the talk that you were giving 2 hours ago, there was the discussion about how we're still going to reach these levels of melt at lower emissions levels or lower temperature levels, but it would take longer. And I'm just wondering how that relates to talking about committed sea level rise. Are we still looking at the same amount of committed sea level rise in the more near future, and then that commitment increases, or what are we?
The commitment up to present is, 20% more than 70 or something like 80 centimeters. Sorry, 27 centimeters from Greenland up to present, or up to. And we can project that increase in commitment, and it in a high emission scenario, it gets above, was it 1.5 meters of commitment? But it's commitment might be better to say the lower bound of eventual sea rise. So all we're delivering is a lower limit. I'm not sure it fully answered your question, but.
That was forgetting the part about the commitment as per current, but then wondering how that tied into the sort of, when you're looking at the projections, I guess the time frame of that commitment.
Yeah,
So you've addressed that a little bit.
we're not clever enough to deliver a reasonable timeline of this commitment because the ice sheet modeling is not yet there. So all we are really doing is giving a lower limit. What that dashed red curve in the IPCC report, which is the low likelihood, high impact curve, that's kind of the upper limit. So I think we're just giving more constraint. And but it seems that ice sheet models need to encode more sensitivity and run at higher resolution, or at least be forced with higher resolution atmosphere and oceans before they can be better. And they probably will be. 10 years from now, they'll be delivering ice faster. But then I guess the question then will be is if we wait 10 more years, is the ice sheet models delivering it faster again? Because if you look back 10, 20 years, it's the same story. Well, partly.
Cool, thank you.
And same with sea ice and snow cover, by the way, in global climate models. They don't melt sea ice fast enough, at least until now, and they don't ablate snow cover fast enough. Right. Thanks, everyone.